Hello again, and I wanted to finish up our Monte Carlo series with probability of making 50% on an option trade. In this case, I want to explicitly say at the beginning a short option trade. I don't think I mentioned this until like halfway through the actual coding part of the video, so I wanted to say that up front. And none of the topics we're going to cover in this video are particularly complicated. However, we're going to string together a lot of things we've done over the past 6 months or so. So on the whole, it's not the easiest of projects. The difficulty combined with the fact that I've had to put this together over several weeks. I've been busy with work and preparing for a major jiu-jitsu tournament, and I really haven't had time to sit down and dedicate stretches of several hours at a time to this. I think the coding section of this video is a little more discombobulated than usual, and I apologize for that. So if there are any questions, please feel free to leave them in the comments. And with that, let's actually start coding. Okay, so let's move on over to a Jupyter notebook, and we'll just enlarge this a tad. Okay, so we have all the pieces already in previous videos to put this together. We have a Monte Carlo simulation of a stock price, which we're going to use here. We're going to use this equation. And from these stock prices, we could get the prices of calls or puts or whatever options we're interested in via a simple Black-Scholes model. And once you have that, it's just doing statistics on the end results. So the only tricky part in here is going to be how do we write this code in an efficient way, and we're going to use a fully vectorized version of this to avoid going over loops, looping over things. So in our video on linear systems, we looked at this stock Monte Carlo problem, and I've opened that notebook already here. And so we came up with this matrix representation of this stock equation here. This is a system of linear equations, and we were able to build a sparse matrix and then solve this matrix equation to get all of our stock prices. So I'm going to be switching back and forth between this old notebook and our new notebook just to make things clear as we go along, and hopefully this won't be too opaque to you. So let's go back to this sparse matrix notebook that we had done previously. So again, we want to build up this linear system of equations that models one Monte Carlo run, one simulation run of a series of stock prices. And this code here, I believe, was 30 days. Yes, 30 days. So we expand this equation like this, so we can get the stock price at the ith plus one day in terms of the stock price at the previous day, and then I just made this substitution to keep the notation a little bit cleaner and rearranged everything so that all of our unknowns are on the left-hand side and all of our knowns are on the right-hand side. So our right-hand side is our initial stock price in this first equation, which is kind of self-evident. The stock price at the initial day is equal to the stock price at the initial day. And then we have all of these rearranged so that all sum up to zero. So we have a system of equations, linear equations, that can be captured as a matrix like this. This is the same as this, just written in matrix form. And again, notice that almost all the entries in this matrix are going to be zero, except for the things on the main diagonal, which are either 1 or -1, and a diagonal just immediately below the main diagonal. To code this up, we used SciPy's sparse matrices, so we don't want to record the fact that all of these, we don't actually want to explicitly store all of these zero values because these matrices are going to get very big, as you're going to see in a moment. So we don't want to actually store all these zero values. And then when we have to calculate the inverse, it's a lot faster to use sparse matrix algorithms to invert this matrix than actually doing it by brute force. So the way that this code worked in our previous one was we defined what these elements of these diagonals would be, and then we passed that, where is it? Where? We pass that in here to build this matrix, and then we just used the built-in linear algebra equations to get this list of stock prices, and then we plotted it here to just see how it works. So this is the code for one stock run, but we want a large number. We're probably going to want like 1,000 runs. So what we're going to do is essentially stitch together a whole bunch of these. Instead of looping over and doing this multiple times, we're just going to stitch all these possible runs together in one big matrix. So if we go back to our new notebook, what we're going to do is, and I've kind of made this in a schematic form here. So what this little image here represents are two matrices, square matrix times a column vector. And that previous code can be represented as like this red block here. So this would be one stock run's worth of matrix information times the relevant column vector, the run for like the 0th to the 30th day, for example. And that will this red blocks represent one run. And then we'd come down here and build a new matrix, and we do this all within our diagonal commands that build a matrix. So we're going to do this quite simply, actually. So our next run would be down here in this colored block here, and then again here and here. So we're just going to stitch together a whole bunch of those matrices to build one gigantic matrix. And this is going to be quite large, and this is why we want to use sparse matrices, because this is going to be very well. We'll figure it out as we actually build the code. So I hope that's not too complicated. Hopefully it'll become clear as we build it. So let's go on to actually coding stuff. So as always, we're going to want to import numpy as np. We want to import scipy, and I'm just going to load in the stats module explicitly from scipy. So from scipy import stats. And just for debugging purposes, I'm going to want to plot some things out. So import matplotlib.plt as plt. Actually, this is pyplot here. Pyplot. And we want to import that as plt. Okay. And then we need to, what is that? The matplotlib inline. So matplotlib inline. Okay, let's run that. Good. So we've already done a whole bunch of Black-Scholes models, so I'm just going to copy and paste from the previous code the equations for the price of a call, price of a put, and then these D values here. So there's no need to really go over that again. So copy, paste. Did all these come in okay? Yeah, they looks like we did. So I mean, these are functions we've used before. Price of a call just returns the Black-Scholes price of a call, price of a put, and then this little function that calculates D1 or D2. There's probably a more efficient way to do this, but since this is, I just want to recycle code just for the sake of simplicity. So actually run that and make sure everything came in okay. Okay, so now let's go on and build the code that's actually going to calculate all of these stock prices. So this is going to be a little bit of the abstract part of things. Okay, I'm not sure if I want to at some point reuse some of this code. So I'm going to put the stock simulation part into its own function. So I'm going to define a function called stock Monte Carlo. And that's going to take a whole bunch of arguments. It's going to take the initial price, let's call that init price. The number of days, let's call that n days. That's the number of days that we're simulating per run. And we're going to need the number of simulations, so that's going to be n sim. What else are we going to need? In fact, let's make this n sims. I think that's more consistent with what I've done in the past. We're also going to need the risk-free rate R. We're going to need the time step dt. Let's actually flip these. Let's go dt comma R. We're going to need the volatility, which is sigma. And I'm going to put in, because I've tested this code out before, and sometimes I want to print out stocks as all those entries as a column vector, or sometimes I want them as a rectangular matrix. So I'm going to create a variable called reshape, and I'm going to set that equal to true, so it reshapes by default. So, up here we're going to invert this matrix, multiply it through to get this column vector, and we want essentially a rectangular matrix where each row represents a simulation, an entire simulation run. So, for example, if we're simulating 30-day runs and we have 1,000 simulations, this will come back. We want to reshape this column vector, which is number of days times number of simulations long, into a matrix that's a rectangular matrix that's number of simulation row. Is that right? Yeah. number of simulation rows, and a number of days is the columns. So yeah, that's going to be our function. Does that look good? I think it does. So let's start building this thing. So the interest rates and the implied volatility that comes into this function are going to be annualized. So we want them on a daily basis. So we want to take the interest rate R and rescale it down by dividing it by the number of trading days in a year. And I'm just going to take that to be 252. So we're just going to ignore weekends and just do trading days per year instead of calendar days per year. And likewise, we're going to take sigma, and that's going to be equal to sigma times np dot square root. Let's see. That's going to be the square root of 1 day divided by the square root of the number of calendar days per year. Again, that's 252. So let's just do this. Since the square root of 1 is 1, let's just do 252.0 and make this a division operation here. So that's good here. Okay, let's move on. So next I need that epsilon value, that random number in our Monte Carlo simulation. So let's do this down here. Epsilon equals np.random.normal. And the size of this matrix is going to be this. It's going to be the number of simulations and the number of days. So let me try to rephrase this. So let's go back up here first, and let's say, for example, we have 1,000 simulations of 30 days. So that's 30 times 1,000 is 30,000, and then we need the 0th day for each of these simulation blocks. So we're going to have to add another 1,000 to each of them. So that's what this does. It's the number of simulation times the number of days. That's going to give us our 30,000 and the numbers I just quoted, and then we need to add to it another 1,000 to account for the 0th day. And I'm going to subtract 1 from it. Just right now I'm just going to subtract 1 from it, and hopefully it'll become clear why we're going to do that. So okay, let's move on from here. From here we just calculate our stock prices, our percent changes in stock prices. So I'm just going to copy and paste from stuff we've done before. I don't really want to dwell too much on this. Backspace. So our percent change in stock price is equal to the risk-free rate times the time step times the implied volatility. We've done this before, and it's just this equation up here. So yeah, okay. Next, now we need to put together our matrix diagonals, and recall back here, where is my actual matrix? The main diagonal is all negative 1s except for this first value here, which is a 1. So if we go back to this notebook here, so all of these values along the main diagonals are going to be negative 1s except for at the very corner of these colored blocks, which will be equal to 1s. So what we're going to do is just set a block initial vector of all negative 1s, and then we're going to go in and like every whatever nsims entries change to positive 1. So let's go down here. We'll just make this, again, I'm just going to copy and paste this from my test code. So here's our vector of 1s, which we call 1s, and that's equal to negative np.1s, and this is the length of that main diagonal there. So, okay, so let's go through and set those corner elements equal to positive 1. So we'll just do that, and that's going to reset all those corner elements to a positive 1. Okay, next. In fact, what I think I'm going to do is just finish out this function quickly and just pass in a small number of simulations and then put in some print statements so we can actually see what these operations are doing, because it's kind of difficult to describe in words all these slicing into the arrays to reset values and whatnot. So I'm just going to build out the rest of this function pretty quickly. Okay, so these are our lambda values from that from this slide here. I just called them ds here, but I referred to them as lambda here. So that's that. This is going to be, this line here is our second diagonal, and this is the remember the sparse matrix command requires the position of each of these diagonals. So this tells this, we're going to pass this in and tell the sparse function which diagonal is which. Now here we actually create the sparse diagonal matrix with the sparse diags command. Here's our vector that contains the diagonals, and here's the indexing element that tells which diagonal as which. So here are, oops, what happened here? Here are the vectors of the known. So this would be the right-hand side of this equation here. So that's this vector here. So it's going to be all zeros except for the first entry of each block is going to be the initial price of the stock. So why do I keep doing that? What's going on? Okay. So now we actually solve the equation, and we do that with the linear algebra sparse matrix solve command. That's straightforward. And now I want to add a block of code to take care of this reshaping of the matrix, because this is a column vector here. And we want, why is my indentations all weird all of a sudden? We want a rectangular matrix. So let's just reshape this thing if the reshape input is set to true. So we just, why does it keep doing this? Okay, so we just do the reshape thing and then return our matrix or column vector as the case may be. Okay, took care of one typo off screen here. I had misspelled true up in this function definition, so I fixed that. So let's go down and quickly create a small simulation so we can actually take apart this function and see what it does. So we need an initial stock price of 100, I think is the numbers I've been typically using. Let's have a strike price of 105. This will be a call option. K equals 105. Let's set the risk-free rate equal to 0.02, so 2%. Let's have the our time step is 1.0. What else do we need? We need a volatility. So let's just say sigma is equal to 0.3, 30%. What else do we need here in this function? We need the number of days, the number of simulations, dtr sigma, and that's it. So let's do 10 days. So let's go n days is equal to 10, and n sim, we're just going to do 5 for now. Let's see if we can actually call this function and there are no errors in this code. So let's just copy all of this. Come down here. Paste. We don't need that colon. Our initial stock price, we called it S0 here, so let's go back. S0 and days is good, and sim, let's make it M sims. DTR sigma, okay, so hopefully this will actually run. So let's run this block. Okay, one error. DT equals 0 or 1. So let's run that. Okay. What's the error here? I called this end day here and end days up there. Run. Okay. Looking good. So let's just go up here and we'll just do S equals. This will be our stock prices, and we're going to print S.shape. So that's the shape of our matrix. As we intended, we have 5 simulations, so there are 5 rows and 11 columns because we're simulating for 10 days, and of course you have the 0th day, the starting day, so that's our 11th. So now that we have that, let's go up here and begin to take this function apart so it's a little more clear how it works. Alrighty, now let's actually zoom in one level more. We can always zoom out later. And we will start with this line here where we pull out all the normally distributed values. So if we're simulating n days and we're simulating n simulation time, so you're going to have n days times n simulation runs, and then we're going to have to add in the starting day for each of those runs. So we're going to have an additional and simulations times 1 addition to this. This minus 1 here comes from the fact that this is these numbers are going to be used off of the main diagonal. So if we go back here and look at the shape of this matrix, this one is going to have all the elements, this vector of ones, and this random number vector is going to be used one below the main diagonal. So you're going to have one fewer element than in this main diagonal. So that's where that comes from. So let's go back here, and you notice that this ones vector here has that does not have that additional minus 1 here. So that's where that came from. Maybe it would have been clearer had I done the ones first and then the epsilons later, but oh well. And one of the reasons I have kind of stumbled over this a bit is I've been using pretty much MATLAB at work for the last year, pretty much exclusively, except for the occasional dabbling in Python to help some of our other offices. So when I was staring at this, I'd forgotten how I had written it once upon a time. Recall that this main diagonal here is mostly, if we go back here, is all negative ones except for this first element. And then since we're stitching together several of these matrices, every time we get to kind of where this first element begins, we have to reset it to positive 1. So that's what this line does. Now, I had forgotten that the difference between MATLAB and Python is that this middle element here in this notation, 0 colon minus 1 colon number of days plus 1, is actually the ending element of our sequence. So in this case, we're going from the 0th element to the last element, and in steps of n plus 1 days. This is reverse of MATLAB. And I wrote the bulk of this code quite some time ago, so I had forgotten that. So if we print out ones here, run that, you notice that our first element is set to 1. They're all minus 1s, minus 1s, minus 1s, minus 1s, and then we get to another plus 1, and so on as we go through that. So let's go back here and get rid of this print statement. Now I found this line confusing, and I had just reviewed my notes from a few minutes ago before I actually started recording this. This sets every entry to minus 1. That is essentially, if we go back here, the next element, if we were to stitch another matrix on here, this element here and this would be, correspond to this one. This would be 1. And the corresponding element for the lambda at that point here would have to be 0. So what we're doing here is actually setting this element to negative 1, because when we come down here and we actually build the array that actually builds that diagonal, we add 1 to it. So that minus 1 plus 1 equals 0. So if we go down here, where we actually build the matrix, and since we're doing 10-day runs, if we print the 11th day, so if we go print, let's see, print, not that, print M11, and we print all the columns. If we run that and run that, let's see here, am I still printing the ones? What's happening? Syntax, oh, okay. Where did I print that? Square bracket, row 11, comma, all columns. And close bracket, close parenthesis. You can see that only has that element 1 on the main diagonal. So this is what it should be. Because I'm printing this out and it's a sparse matrix, I'm only printing 1 row. So this 0th 0 column corresponds to the fact that this is only a 1 row by 11 columns. So it's confusing, but you got to sit down and think about it for a while. Okay, let's go back up here and get rid of this print statement. Okay, this p vector is our vector of prices, which should be pretty self-explanatory here. That's this vector here. This is all zeros except for the initial one, which is our stock price. So if we stack these up, we're going to have another S0, 0, 0, 0, 0, 0. We get down here, it's S0 again. So what we've done here is created a vector of all zeros, and then using the same syntax that we used up above here for ones, we just reset that initial value to the initial stock price. And that's that. We just go through and we solve the equation. We don't need the matrix inverse, so we just solve the equation directly, reshape it into a rectangular form, and then return it. So that's that. Let's go on now and actually work out the option prices and then the probabilities. So let's go down to a new cell here. Do we need this print command? I don't think we do. Let's get rid of it. Man, it's a rare rainy day here in Los Angeles, and it's really coming down. So we're going to need the time. So that's going to be, I'll just call it T days. And I want to have the days actually count down from whatever our number of days is to 0. So I'm going to count from n days. Let me make sure I type this right. Down to 0, and since Python kind of truncates it one short, we have to go to -1, so it'll actually end at 0. And yeah, okay. Okay, and something looks, oh, I need to actually tell it we're counting down backwards, so I need another -1 here. And the time that goes into the Black-Scholes model is years, so I'm just going to divide this by 252, the number of trading days per year, to convert this number down into years. Let me just see if that runs, no typos. Yep, okay. So our D1 and D2 values, oops, this needs to go down one line. D1, comma, D2 is equal to our D function. Where is that defined? Right here. So let's just copy this. Copy. Paste. This will operate element-wise on the function. So let's go. Let's see here. Our stock prices are capital S. This would be K. Risk-free rate, time step, and implied volatility. That looks good. Let's just see if that runs. It does not. What's the issue? S is not defined. Why is S not? Oh, is this not a capital S? Let me make it a capital S. Oh, still an issue. What's the problem? Oh, it's T days now, right? Instead of just regular T. T days. There we go. We get a divide by 0 error, but that's not going to be an issue. So, okay, so we have that. Let's do the same thing for a call price. Where's my call prices defined? Put price, call price. Copy. Let's call this C is equal to paste. Let's not make the same mistake here. T days. Does this run? No, it does not. What's the issue? Norm is not defined. So where are we pulling in the stats? Let me see. Just run through all these cells here. Yeah. Okay, I got to pull in norm explicitly or put in the stats command. So where are our imports? Import stats. Let's go from, let's do this, from scipy.stats import norm. Does that work? That work? There we go. So now let's visualize this and see what we get. So for I in range 0, comma, well, we don't need the 0. Let's just do n sims plt.plot. Our call, each row, our call price is a C. Each row is a run. So we're going to print out the ith row and all columns, colon, and we need the times, don't we? So T days, and since this is in years, we need to put it into days. So times 252. Now I think this is going to have an issue Yeah, there's our plot. It's essentially plotting it backwards. So we actually need to set the limits from from 10 down to 0. So let's go down here, and in this case, let's do plt.xlim. Let's go n days comma 0, and let's run that. That looks about right. So now this is only a 10 simulation, so let's do something a little more realistic than this. So let's go, instead of 10 days, we'll do 30 days, and instead of 5 simulations, we'll do 1,000. Run, run. Okay, that plot is a mess. So let's do this. Let's put in let's make these lines transparent. So let's come down here and go alpha is equal to 0.05. Will that do? That looks a bit better. So what we have here is all of our calls start out at the same price because all the 0th day of the stock simulation. And most of them, as you can see, go down to 0 or close to 0. And then some of these trades are going to be losers since we're assuming we're selling a call. We're doing a short call here. Some of these actually blow up against us quite bad. So let's now actually calculate some probabilities in this. Before doing probability of 50%, let's just do probability of making a profit at all. So we'll define a profit as 1 penny. And to help with the conceptual ideas and printing these things, let's again switch this down to 10 days and 5 simulations. So the statistics that come out of this part initially are not going to be that good, but it's easier for diagnosing issues here. We'll keep the transparency here. The fact that there's only 5 lines in here is what's causing this issue here. But okay, so let's go back here and put in some lines. Our initial call price, let's go call it init price, is equal to the 0th column of that C matrix. And those should all be the same number. So what I'm going to do is just take the 0, element out of that. Okay. And let's create a variable called losers and winners. So losers and winners. And we're going to have these be logical vectors. So we're going to define losers are when our final call price is greater than the initial price we sold it for. So let's go here, let's go C. So we want to do all rows and the last column. And we want that, let's see, we want to know, it's a loser if it's greater than or equal to our initial price, init price. And likewise, our winners is going to be when it's less than or equal to our initial price. So winners is equal to C, all rows, last column, and that is less than or equal to our initial price. Let's see if this runs. Good, no typos. Let's print out the number of losers. Let's actually print out just the losers vector itself now. So print losers. What's wrong here? I spelled it wrong. Print. Come on. Losers. So here we go. False, false, true. So we have one loser in this particular run. So what we could do to get the number of losers is just sum up this vector here. So let's do number of losers is equal to sum losers. And let's just print number of losers. Run that. So as we suspected, 1. It takes the falses as zeros and the trues as 1 and then sums them all up. Okay, so let's do the same thing and let's just get rid of this print statement here. Oops. This print statement here, and we'll do the same thing from the number of winners. So number of winners is equal to sum winners. There we go. Let's just run that. Of course, I have a typo. What did I do wrong here? Oh, I spelled winners wrong. Come on. Winners. There we go. Okay, so the probability of making a profit is the print. It's going to be our number of winners divided by the total. So the number of losers plus the number of winners, but that's just our total number of simulations. So it should be n sims. And in this case, 80%. And since we only did 5 simulations, and one of them happened to come out a loser, so it's 1/5 is a loser, or 4/5 is our winners, or 80%. So if we actually run this simulation again, we should get slightly different numbers. Not in this case, but for a large number of runs, you probably will get slightly different numbers per iteration. So let's go back to this print statement here. Print. And let's just put in probability of profit is equal to that. Let's just run it. There we go. Okay, let's do probability of making 50%. And before that, let's just go back up here and reset these to more reasonable numbers. So 30 days, 1,000 simulations run, and our probability of profit's about 73%. So that's a reasonable number. Okay, one thing I want to do first is go back and set this down to a smaller number of simulations again. So we'll go back to 10 days and a total of 5 simulations instead of 1,000. One thing I didn't explicitly say is that this probability of profit is at expiration. And when we do probability of 50%, we want to consider the possibility that any time during the span of which that contract is valid, we hit that 50% target. So that's going to be a little bit different. So I'm going to go back and do fewer number of simulations just so we can actually print out some things and make sure we're understanding how we're building these summations. Okay, so for this I just want to actually comment out these plotting statements. Okay, so our target price is half of our maximum profit. So our maximum profit is obviously the price at which we sold the option for. So let's say half max is equal to init price over 2. And now we need to search our matrix of call prices for whether or not that condition has been met, whether we are reached the price target of that half max variable. So let's create another variable called reached half max, and that's going to be equal to half max is less than or equal to, C, our matrix of call prices, is less than or equal to half max. So let's run that and make sure there are no typos. Okay, that looks good. So let's print out that matrix there. So here we go. We have a matrix of trues and falses that should be 10 columns by 5 rows. And we need to see if at any point during each of these rows this is this true. So we do that. There are a couple ways to do that. The way I'm going to do that is by summing over this matrix in a column-wise manner. So I'm going to just use the same variable name, reached half max, and that's going to be equal to mp.sum of reached half max. And we want to explicitly sum over the column. So I'm going to say axis is equal to 1. So that'll explicitly sum over the columns, and now let's print out that result. Since we're using the same variable name, we can just copy, paste, let's run it. So you can see we have an array, for example, that will tell us which of these rows is that condition is met. So like in this last row, this last row is entirely false, so this should sum to 0 and be 0 here. This second row here is also entirely false, so that's this 0 here. So we have 3 times in this simulation where we've reached our target and 2 times where we have not. So now we just need to turn that into a probability, and we'll do that just by summing up all these entries that are where this is not equal to 0. So we'll do another comparison operation, and where these come out to be true, we'll just sum those up and divide by the total number of simulations. So let's define that variable as, let's just call it probability. That is equal to np.sum, and we want to sum up reached half max is greater than 0, so that's our Boolean operation. Let's see, does that run? Good. And let's print out that probability. Print prob. Oh, that's the number of elements that was non-zero. So we need to divide that by the total number of runs. So prob is equal to that divided by n sims. And in this case, 60%, which is true. So let's go here and just add some text here. Probability of making 50% is equal to that. And let's get rid of these kind of debugging print statements. I'm just going to comment them out for the time being. Okay, let's go back here and change these number of simulations and days to, again, more reasonable numbers. Where? Here they are. So let's go 30 days, and let's do 1,000 simulations. Run. So the probability of making 50% in this case is 83.6%. Okay, I want to call it quits at this point because this has gone on way longer than I really wanted it to. I intended to go on to do short puts and maybe a strangle or call spread or some more complicated strategy, but I think I will do that on in a follow-on video, and for this one we will just call it quits, and I will see you guys later.